So, what we have seen till now, the frequency modulation and phase modulation, and collectively they are called as angle modulation. So, equation of FM can be written like this, that we know, and angle of PM phase modulated signal is written like this. So, for this let us just discuss a few points or few definitions which you have used. What is the frequency deviation? We know that frequency deviation is directly proportional to your basis signal for FM signal. Okay? And proportionality constant is Kf, that is phase, that is frequency sensitivity, and the units is hertz per volt. And instantaneous frequency we can write, because phase deviation is nothing but instantaneous frequency of the FM signal minus frequency of the carrier signal. So, instantaneous frequency is C plus KFMT. So, what would be the instantaneous phase of the FM signal? We can directly see this is the instantaneous phase, right? Instantaneous phase is 2 pi FCT plus 2 pi KF integral ut. So, what is the phase deviation? Phase deviation for FM signal is instantaneous phase minus phase of the carrier, right? Because you are modulating your carrier AC cos 2 pi FCT with MT, right? MT is modulating your carrier AC cos 2 pi FCT. Delta theta, the phase deviation will be 2 pi KF integral mu d. And for case of PM, we know that phase deviation is directly proportional to your masses signal, right? So, first for the PM signal, the phase deviation is theta it minus theta minus 2 pi FCT, and that is directly proportional to your MT, which is KPMT. See, any angle modulated waveform has a structure like this, right? So, theta it for the case of FM is this. So, we replace theta it by this and it becomes a FM signal. And if we replace, okay, so now we go to instantaneous phase. What is instantaneous phase? For the FM 2 pi FCT plus KPMT. So, if we replace our instantaneous phase theta it with this equation, it becomes a PM signal, that we have discussed in our previous classes. This is your general structure of an angle modulated waveform, or you can see, you can understand it like this, that you are using your message signal MT, which is modulating your AC cos 2 pi FCT carrier signal, and it will give you AC cos theta it either FM or PM depending on the nature of the instantaneous phase. If your instantaneous phase have this type of nature or this equation, it will give you FM, and if your theta it depends, follows this equation, it will give you a PM signal. So, what is the frequency deviation, or what is the instantaneous frequency for this? We know that instantaneous frequency is nothing but 1 upon 2 pi d theta it by dt. So, instantaneous frequency for the PM signal is just if we Fc plus Kp by 2 pi m dot t. So, the frequency deviation for the PM signal would be Fit minus Fc, that is Kp 2 pi m dot t. So, as you can see from here that frequency deviation for FM is directly proportional to Mt, but for PM signal frequency deviation is proportional to derivative of the message signal. So, this we have seen in our very first class where we discussed angle modulation. Now, here see all of these equations are true for any MT, right? So, if your MT is a tone, by tone I mean It is a sinusoidal signal. It is either a sine of frequency FM or it is a cosine of frequency FM. Then these parameters, these frequency deviation and phase deviation, you can evaluate, right? Okay, let's take if your message signal is AM cos 2 pi FMT, FM PM. Frequency deviation delta F for FM is KFMT, right? KFMT. So you can write KF AM cos 2 pi FMT. If we define a new, we are interested in finding the peak of the frequency deviation or maximum frequency deviation. Means we first take absolute value and then we find out what is the maximum value. So peak frequency deviation for FM will become, when your message signal is this tone, KF AM, right? Because you take absolute value of this, so it will be KF AM. And what would be the frequency deviation for this PM? Kp by 2 pi, Kp by 2 pi, you derivate it, right? So 2 pi FM sine of 2 pi FMT. So Kp FM sine of 2 pi FMT. So what would be the peak value of this or maximum frequency deviation for FPM? It will be Kp FM. Similarly, what would be the phase deviation for FM signal? It will be 2 pi Kf integral of this. So if we integrate actually this integral if you integrate it 2 pi Kf sine of 2 pi FM T divided by 2 pi FM, it is very straightforward, just you integrate it. So it will be Kf AM by FM and sine 2 pi FMT. And what would be the frequency, the phase deviation for case of PM? It is simple, KPMT. KPMT means Kp AM cos 2 pi FMT. So if you are interested in the maximum or peak value of frequency deviation, so delta T magnitude max for case of FM and PM would be Kf AM by FM and it will be Kp AM. So as you can see, the frequency deviation or peak frequency deviation does not depend on the frequency of the message signal here, but it depends on the frequency of message signal for case of PM. Okay? So this thing we have discussed. Yes. This quantity is also known as modulation index. The max max phase deviation is also known as modulation index, and modulation index is only defined when your message signal is of sinusoidal type. So, this thing you should remember. So, value of modulation index is kf am fm for frequency modulation, and it is kp am for the modulate for the PM. So, you can also write your delta F max in terms of your modulation index, right. So, it will be beta Fm, because beta is Kf Am, beta by Fm, sorry, beta is Kf Am by Fm. So, no, it was right previously. So, beta Fm. kpam, sorry, I have missed am here, correct. So, it will be beta Fm, right. So, this is the some points which you must remember, and always remember that modulation index is only defined for the sinusoidal type of message signal. Though all these instantaneous frequency, frequency deviation, max frequency deviation, all of this is defined for all the message signal or any arbitrary message signal. Okay. So, next we studied the bandwidth or the spectrum of the FM signal, and we have seen that the bandwidth of the FM signal or PM signal is ideally infinite, right. But what is the practical bandwidth of any FM or PM signal? By practical I mean if you see any FM signal, it will have so if it is a frequency spectrum, magnitude of the frequency spectrum of your FM signal, all the frequency component will be there, as we have seen in our previous class. But there will be some bandwidth where most of the energy will lie. So, if 98% or 99%, 97% of the energy of the whole signal lies within some particular range, then we call it a bandwidth. We give a definition that 98% of energy of the signal lies within this range, then it is a bandwidth. We define it as a bandwidth practically, because if you just neglect these signals, it will carry very little information or little energy. So, you will not lose anything, because you cannot give the whole spectrum, you cannot allot the whole spectrum in order to transmit one FM or PM waveform, right. So, there is a formula, Carson's rule. I am just stating it without proof, that bandwidth of a FM or PM signal is 2 times D plus 1 W, where W is the bandwidth of the message signal. So, for any arbitrary message signal MT, which is band limited to W, the bandwidth of the FM modulated waveform. So, what MT is modulating your AC cos 2 pi f CT, whether it is either give you FM signal or PM signal. As I told you, it will have this type of structure where theta I t will depend whether you are generating a FM signal or a PM signal. So, if the bandwidth of this FMT signal is W, then the bandwidth of this practical bandwidth will be 2D plus 1 W. But what is D? D is deviation ratio, and it is defined as maximum frequency deviation of FM PM waveform divided by the maximum divided by the W, bandwidth of the message signal. So, this is the practical bandwidth of your FM PM waveform, that most of the energy will lie within this bandwidth. So when your as you if you remember, okay, so let's focus when your MT is a tone signal, then what would be your bandwidth? Bandwidth is 2 times D plus 1 into W, right? Bandwidth of the FM PM signal. W is FM here because this is single tone and the frequency component is at FM. What is D? D is max frequency component, sorry, maximum frequency maximum frequency deviation divided by FM. So maximum frequency deviation, if you remember, maximum frequency deviation is, we have evaluated it, right, somewhere. Correct. It is beta FM, right? So D is beta FM, which is beta. So when your message signal is sinusoidal, your bandwidth is 2 times beta plus 1 into FM, where beta was modulation index. If you remember, your beta is modulation index, and we have defined beta as somewhere we define beta, right? Yeah, Kf AM by FM. For FM signal, where your beta is, where your beta is Kf AM by FM for FM signal and Kp AM by, and you can also derive beta from here, that what is the maximum frequency deviation divided by the FM. So beta is max frequency deviation divided by FM. Why I am particularly writing FM here? Because beta is only valid for, only defined for the tone signal. So this is the frequency of your tone. So they are analogous, right? Analogous. In case of tone message signals, we use beta, and for any arbitrary, any other message signal, we will use D. Okay? And W is bandwidth of your message. Always remember this. So this thing we have studied. This is a new thing which we have introduced. We have not studied it earlier. That what is the practical bandwidth? Theoretically, we have seen there will be all frequency components, frequency of all from FC, I mean to FC. We have seen it, right? But most of the energy will lie within this bandwidth, which is called bandwidth, which we evaluate using Carson's rule. Okay. Next we saw or studied the narrow band FM, and while studying NBFM, we have seen that if your signal satisfies this, then your FM PM signal satisfies this, then you are actually having a NBFM signal. And what was your CF? CF we defined as 2 pi kf, and AT we defined as integral of your message signal. This is for the case of FM, and for the case of PM, you can just replace CF by KP and AT with MT for P. So this is a narrow band assumption, right? So if your message signal is a sinusoidal signal, then you can see that this assumption is same as 2 pi kf integral of AM cos 2 pi FMU du I am just integrating. So after integration we will get this kf am, because sorry we forgot to put this max of CF80 should be less than equal to 1, and if you evaluate max of this it is 1, so kf am by fm. And if you remember, this was nothing but modulation index for fm. And similarly, if you derive it for pm, you will have, let us do it for pm, CF is Kp, it is your mt, and for case of sinusoidal signal, this is Kp in the max, sorry, I always forget to put max. So it is Kp am, and this is nothing but modulation index, if you remember. This was the modulation index for pm. So this modulation index actually unify both fm and pm. That if for the case of tone signal, if your modulation index is less than equal to 1, then we call it a narrowband FM. So narrowband FM means beta is quite less than 1, and if you remember the definition of beta, beta is max frequency deviation divided by the frequency of your tone, correct? Just go back and see, this is your kf am by fm, this is beta, and your beta is defined like this. Your beta is, see, if you can see from here, delta f max divided by fm. So this is your beta. So you can see that max frequency deviation is quite low for the case of a narrowband FM signal. So if you want to generate a wideband FM signal, so if this is a narrow band, means wideband means which do not satisfy this condition, correct? So delta F max is quite large in that case. Okay? So delta F max is quite large, or the maximum frequency deviation of a wideband FM signal is quite large as compared to narrowband FM signal. So, okay, so let us discuss one more thing. What was the bandwidth? If you remember, 2d plus 1 into w for any arbitrary MT, and it was 2 beta plus 1 into w into fm when your message was a sinusoidal signal, correct? So if your beta is quite low, then bandwidth is 2 fm, and when your bandwidth is, when this is narrow band bandwidth, and wide band mein, when your beta is quite large, 2 beta, because you can neglect 1, in that case it will be 2 beta fm, and for when your beta is quite less than 1, you can neglect beta because 1 is quite large, then for narrow band it will be 2 fm. So this thing you should remember. And similarly, you can say that bandwidth of a narrow band signal for any arbitrary MTs 2W, and wide band bandwidth of a wide band signal for will be 2 theta. Okay. So what till now we have seen that what is the structure of your FM signal and various definitions. We have seen that when your message signal is a sinusoidal signal, this we can also write it in this form, all the definitions. Then we have seen the bandwidth, the practical bandwidth of a FM PM signal. Okay? in terms of D for case of any arbitrary MT, and in terms of beta and FM in case of your sinusoidal signal. And we have seen the narrowband assumption, because in our analysis we have shown that any FM signal which satisfies this will give you a narrowband FM, right? And you can equally convert this inequality or this condition in terms of beta, and you say beta should be less than equal to 1 and beta should be greater than equal to 1 for WFM. And we have seen that for NBFM delta F max is quite high, means maximum frequency deviation is high, and for case of WBFM maximum frequency deviation is low. So this is the difference